Okay, so before the fall break, we started this topic, earth moving materials and operations. And then we discussed about the earth moving operation, which includes the excavating, loading, hauling, placing, compacting, grading, and finishing. Can you hear me well?
Yes, everything's fine.
Okay. Then we discussed about some of the factors about the equipment selection. And after that, we started with some basic definitions. First of all, the definition of the production, and then the cost per unit of production. Then we talked about the site conditions, good, excellent, fair, and the management conditions, good, excellent, fair, etc. Poor as well. And then we discussed very briefly about the major types of soils. So starting from the rock to the clay, okay, and then also their characteristics, trafficability, and the loadability. So we see that which types of soil have the good trafficability and which types of soil have the good loadability. And then we talked about the moisture content of the soil. So how we can calculate the moisture content in the soil. And then different soil classifications, gravel, rock, sand, boulder, cobbles, silt, clay, organic soils, etc. So their classification is mainly based on their particle size. And then the sorry, my throat is. Then the classification of the soils based on the unified system. Okay, poorly graded sand, well graded sand, low plasticity silt, low plasticity clay. So we had a number of such classifications of the soil, and their drainage properties, construction workability, suitability for subgrade, and suitability for surfacing. So all of this has been recorded, is available in the recorded video. So you can, if you have not had a look at it, then you can see that recorded video as well. So we said that how these properties are changing. Next is the next we talked about the soil conditions, the bank conditions, loose condition, and the compacted condition. So bank condition is the natural state before disturbance. Loose condition is when the soil has been excavated or loaded into the some truck. And the compacted condition is that when the soil is the excavated soil has been placed back, and then some compaction has been provided. So BCY, LCY, and CCY, or BCM, LCM, and CCM are the relevant terms. So for example, if you take the SI system, so we will use the bank cubic meter. That means the cubic meter of the soil, the volume of the soil in the bank condition expressed in cubic meter. And similarly, LCM and CCM for loose cubic meter, CCM for the compacted cubic meter. So based on these properties, we have certain characteristics of the soil. Swell means when the soil is removed from the bank condition, the soil expands. Okay, so that expansion of the soil is called as the swell, and that swell is measured in terms of the percentage. And we did one example for the swell as well. And then the shrinkage, and the shrinkage is when a soil is compacted Some of the air is forced out of the soil's void spaces. As a result, the soil will occupy less volume than it did under either the bank or loose conditions. So this phenomena, which is the reverse of the swell phenomena, is called shrinkage. Okay. So remember that this type of shrinkage, and you also see that in concrete, which is another construction material, in concrete also there is a shrinkage as well. This shrinkage or the concrete in the shrinkage, they are different in a way that the concrete in the shrinkage in the concrete is a natural process. Okay, when the concrete dries up, and then due to the decrease in the moisture content in the concrete and then some other factors, in a natural process, the concrete shrinks. However, this shrinkage of which we are talking about over here is not a natural process. It is as a result of the compaction. For the compaction, we have to apply the force on the soil. Okay, so this is the difference between the shrinkage. So shrinkage, when the soil is compacted, then the void spaces in the soils are removed. So that's why the density of the soil increases. So shrinkage, that means the percentage change in the volume in the case of the shrinkage will be then that will be equal to the 1 minus the weight per bank volume, weight per compacted volume multiplied by 100. So this formula is similar to the formula for the percentage of swell. Okay, weight per bank volume, but weight per divided by loose volume minus L, because in this case the weight per bank volume will be higher than the weight per the loose volume. Okay, in the loose volume, the weight the weight will be less, the density will be less. So that's why, just to provide a positive answer, we have described the same formula but in a different way. Okay, so formula is the same. Okay, so shrinkage percentage. So as an illustration, you can see that the soil is removed from the bank condition and then put it into the truck. That is the loose condition, and then that soil is used for placing in some, maybe as a subgrade material for the highway construction, or to provide the required level on a construction site, and then compacted using some compactors. Okay, then the soil will be in the compacted condition. So as an example, if you can say that if the soil whose volume was 1 cubic meter in the bank condition, in the loose condition, if its swell percentage is like 25%, so its volume will become 1.25 cubic yards. That's for the same weight of the soil. Then when you will compact it, so to get the desired level of the density, to get the desired level of the bearing capacity of the soil, so the volume will decrease. So that means soil will be in the compacted state. So as an example, it may be like 0.9 cubic cubic yard of the soil in the compacted situation. So example 2.2, find the shrinkage of a soil that weighs 2,800 pound per cubic yard, or 1,667 kilogram per cubic meter in its natural state. That is the weight of the soil. This is the weight of the soil in the bank condition. Okay. So this is the weight of the soil in the bank condition. Okay. bank condition, and then after in its natural state, and 3,500 pound per cubic yard or 2,077 kilogram per cubic meter after compaction. So just apply it into the formula. So this is the bank condition, this is the compacted condition. In either units, I mean, the answer will be the same, okay? Whether you will use the cubic yard or whether you will use the pound per cubic yard or whether you will use the kilogram per cubic meter, the answer will be the same. So in this case, the answer will be 20%. So 20% is the shrinkage percentage, okay? So how to interpret it? Hence a one bank cubic yard of material will shrink to 0.8 compacted cubic yard as a result of the compaction. So 20% means there will be 20% reduction. The remaining will be 80%. So a 1 cubic yard will shrink to 0.8 cubic yard material. Okay, so next is the load and shrinkage factors. I think we covered this last time, but anyway. Now, I think from here we can start from today. Okay, load factor. So because Hall unit and spoil bank volumes are commonly expressed in loose measures, it is convenient. It is convenient to have a conversion factor. It is to have a conversion factor to simplify the conversion of loose volume to bank volume. So the factor used for this purpose is called as the load factor. Okay, so yeah, so this is just the ratio. I mean, this is just the same formula as before, but just we have said that the weight per loose unit volume divided by the weight per bank unit volume. So instead, in this, we can call it as a load factor. So for example, if in the previous formula, so what was the formula for the swell? So if I represent swell by, S, and remember that in this previous formula, okay, so just maybe swell is like this. A weight per bank volume, weight by loose volume, okay. So, sorry, yeah. So the yeah. So the load factor. So weight by bank volume, weight by loose volume. So the swell formula is basically the load factor minus 1, right? Swell formula is a load factor minus 1 multiplied by 100. So that is the load factor. So for example, over here, what is this load factor? Weight per loose volume divided by weight per bank unit volume, okay? So this is the load factor. So yeah, so the swell percentage is weight weight per bank volume minus the weight per the loose volume and multiplied by 100. Okay, so since this was in the terms of the percentage, so we can take divide by 100 on the other side, and then we can get this formula in terms of the swell and the shrinkage. So anyway, so the load factor is basically the ratio of the weight per loose volume and the weight per the bank unit volume, or it can be also related with the swell. So load factor is equal to 1 over 1 plus the swell. So it's very easily we can derive it. On the other hand, we have the shrinkage factor, a factor used for the conversion of the bank volume to the compacted volume, is sometimes referred to as the shrinkage factor. So bank to compacted, okay, shrinkage factor, okay, and then Previously, here we can say that and then here is the load factor is what? Commonly expressed in loose measure. It is convenient to have a conversion factor to simplify the conversion of loose volume to bank volume. Okay, so the loose volume, so loose volume, that is the in the loose condition, to the bank volume. So that is the load factor. Okay. So the bank volume may be multiplied by the shrinkage factor to obtain the compacted volume, or compacted volume may be divided by the shrinkage factor to obtain the bank volume. So the shrinkage factor is the weight per the bank volume divided by the weight by the compacted unit volume, or shrinkage factor is equal to 1 minus the shrinkage. So these terms are just for our convenience only. Otherwise, if we understand the shrinkage, or if you understand the swell, then the shrinkage factor and the load factor are similar in those terms. So that's why these terms have been related with each other. So for example, the shrinkage factor has been related with the shrinkage, and the swell factor has been related with the load factor as well. Okay. So from loose to bank, load factor, and then from bank to compacted, that is the shrinkage factor. Okay. So bank volume and then the compacted volume. So for example, over here, this is if we have 3 boxes, that is the bank, that is the natural state, then loose, and then compacted. So so from bank to compact, that is the shrinkage factor. Okay, because from the bank condition to the compacted condition, the volume decreases. Okay, and the load factor means from the loose to bank. Okay, from the loose to bank, that means how much is the load factor. That means that we have to apply. Okay, so from the loose to bank, and the bank to compacted. Okay. Okay, so now let's apply this into this equation. A soil weighs, yeah, I say for convenience, I will only use the kilogram or the SI units. Okay, a soil weighs 1163 kilogram per LCM. What is LCM? Yes, what is LCM? Hello? What is an LCM? LCM. Are you here?
Yeah, I just don't remember, honestly.
Okay. And how about others?
I don't know.
Sorry?
Least common multiple.
Yeah, but that is the mathematics term, least common multiple. But here we are talking about the construction management. So LCM is the loose cubic meter. Loose cubic meter. Loose cubic meter. That means in the loose condition. Okay, that means when the soil has been excavated. Okay, and what is BCM?
Bulk cubic meter.
Not bulk cubic meter, it is bank cubic meter, bank. Okay, and then, and what is CCM?
Compacted?
Yeah, CCM is compacted. So now I think you are getting the point. Okay, compacted cubic meter. So first of all, so what we have to find over here is that find the load factor and the shrinkage factor. So based on this information, find the load factor and the shrinkage factor. So we have three values. One value is 1163. So this is the LCM. And the other value is 1661. And this is the BCM. And the other value is 2077, which is CCM. Okay. So if we want to find the load factor, so load factor is from, I just described that load factor, we go from loose to bank. Okay. So loose cubic meter divided by the bank cubic meter. So loose cubic meter is 1163. Bank cubic meter is 1661. Yeah, over here. So it is 0.7. And then the shrinkage factor is, for the shrinkage factor, we go from bank to compacted. So the shrinkage factor is 1661 divided by 2077. Okay, so it is 0.8. So this is how we can calculate the shrinkage factor and the load factor. Okay. In part B, how many bank cubic yards or bank cubic meters and the compacted cubic yards of materials are contained in 1 million loose cubic yards, of this soil, or 593,600 cubic meter of the soil. So how many bank cubic yards are contained? Okay, how many bank cubic yards? So for example, if we want the bank volume, okay, if we want the bank volume, so then that means we will use the, so for example, if we want to use if we want the bank volume, so for example, bank volume, so we will use the loose are contained in the loose condition. So what is the formula which what is the formula which relates the loose volume with the bank volume? So it means that if we have the loose volume as 593,300 cubic meter. So in the bank condition, it will be multiplied by its load factor. Okay, because the load factor is the one which relates the loose condition in the bank. So that means we will have to multiply it with 0.7 to get the volume in the bank condition. So it will be 415,310 bank cubic meter. Okay. So that means 593,300 cubic meter volume in the loose condition will be equivalent to 415,310 cubic meter. Similarly, in the bank condition, if the volume is 415,310 cubic meter, in the compacted condition, this volume will be 333,248 cubic meter. Here we will use the shrinkage factor. Okay, so therefore you can see that if we know the shrinkage factor and the load factors available, so we can convert from one type of volume to another type of volume. Okay, we simply have to multiply the respective condition, the volume in the respective condition with the either the load factor to the shrinkage factor to find the answer. So we will, if we want to find the volume in the bank condition, you will use the load factor. You will multiply the loose volume with the load factor to calculate the volume in the bank condition. Or if we want to find the volume in the compacted condition, then you will multiply with the shrinkage factor the volume in the bank condition. Remember that these are the ratios for the weight per unit of the volume. Okay, weight per unit of the volume. These are not the ratio of the volumes. Okay, so the volume is on the opposite. Okay, so mathematically these formulas, if you want to understand these formulas mathematically, so you will take the ratios as weight per volume. Okay, not the volume to volume ratios. Okay, so the load factors. So soil volume change characteristics, table 2-5. So typical soil weight and volume change characteristics. So for different types of soils, we have found that we have these typical values. So for example, if you say that, if you take the example of clay, clay in the loose condition will be about 1,370 kilogram per cubic meter. In the bank condition, its typical unit weight will be 1,780 cubic meter. In the compacted condition, it can be about 2,225 cubic meter. So if we use these typical values, then we can calculate that its percentage swell will be 30%. Its shrinkage will be about 20%. Its load factor will be 0.77%, and its shrinkage factor will be 0.8%. Okay. The common earth. So a common earth will be a mixture of clay, silt, and sand. Okay, so that is called as the common earth. So the common earth is relatively heavier in the bank condition than the clay condition, but in the compacted condition, it will be relatively lighter. Okay, so the clay can be compacted better than the common earth. Similarly, the blasted rock, we have this type of situation. Sand and gravel, we have this kind of situation. So you can say that various types of soils will have similar conditions. Okay, have some various types of soil will have slightly different conditions in the different unit weights in the loose, bank, and the compacted volumes. So a typical data for these types of soils may be very useful for later on. calculations. Okay, now let's talk about the spoil banks. So what is a spoil bank? So when planning and estimating earthwork, it is frequently necessary to determine the size of the pile of material, size of the pile of the material that will be created by the material removed from the excavation. So if the pile of the material is long in relation to its width, it is referred to as a spoil bank. So especially in a highway construction, so some of the material may be removed along the length of the road, and then that material, that means the soil and the rocks, will be placed along the length of the bank. So that is called, that type of placement of the material will be called as the spoil bank. So if the material is dumped from a fixed position, a spoil pile is created, which has a conical shape. Okay, so that means if for example, the soil is placed from a position, so then the soil will the soil will take the shape of the form of a cone. Okay, so that cone, a conical shape, will be the shape of this spoil bank. And then if we continue it in a longer manner, then lengthwise this type of shape will be extended. So a spoil's angle of repose is the angle that the sides of the spoil bank or pile naturally form with the horizontal when the excavated soil is dumped onto the pile. So for example, if the soil is being dumped into the pile, into this pile, so that means the truck comes from here and then dump the soil over here, the soil will stand in its natural condition at some angle. Okay, at some angle. So this angle is called as the angle of repose. Okay, so this natural angle which it makes with the horizontal is called as the angle of repose. So the angle of repose, which represents the equilibrium position of the soil, varies with the soil's physical characteristics and its moisture content. So normally, if for example, if there is a clay, the angle of repose will be high, especially when the clay has some moisture in it. Or if it is the sand, the angle of repose will be less because the sand is quite a loose, and then especially when it is dry. So the angle of repose for the sand will be less. Angle of clay as repose for the clay will be high. So the angle of repose is the angle that the sides of the spoil bank or pile naturally form with the horizontal when the excavated soil is dumped onto the pile. So this table then gives some typical angles of repose. So for example, the clay, the angle of repose will be typically 35 degree. For a common earth in a dry condition, it will be about 32 degree. For a common earth in the moist condition, it will be about 37 degree. Gravel, because gravel particles are slightly bigger, so they can support each other in some natural state, so its angle of repose will be 35 degree. But sand in the dry condition, its angle of repose will be less. So they can see that the angle of repose, that means the ability of the soil to stand in their natural state, the angles change from something between 20 and 30 degrees. Okay, so the sand in the moist condition will have also some angle of repose as well. Okay, so spoil banks. So if then we have the if the soil then if the soil when it is dumped, okay, soil when it is dumped, that means, so then the soil will stay in some triangular shape. Okay, So that is called as the triangular spoil bank. And for that triangular spoil bank, you can say that because it is in the form of a cone, so we can determine its volume by using the geometrical shape of the geometrical properties of the cone. Geometrical properties of the cone. So if we know that this much volume of the soil was dumped, then we can find the width of the base, and also we can find the height of the and we can also find the width of the base and the height of the spoil bank. So here B is the base width, H is the pile height, L is the pile length, okay, and R is the angle of repose, and V is the pile volume, which is in the cubic meter or cubic feet. Okay, so in this case, then we can find the by this formula. So this formula is nothing but the application of the geometry to calculate the volumes of the shapes. Okay, so by using some by using the principles of the geometry, we can easily derive this formula. So I'm not going into the derivation of this formula, so it's very but you can do it very easy over here. So this is the triangular spoil bank. So we have two types of spoil banks. One type is the triangular spoil bank. That means for the case of a highway. So for example, if this is a highway, okay, so that means on the length of on the side of the highway, if there's some excavation material has been placed over here, so then in a very long length manner, then the spoil bank is created. So this is the length. That means if we take this much length of the spoil bank, so that is over here, length of the spoil bank, and then that will be the width, and this will be the height of the spoil bank. Okay, so yeah, this is the width, height, and length. So if we know the width, height, and the length, and then we can easily find the total volume, or if we already know the total volume, then we can find the width of the spoil bank and the height of the spoil bank. And angle of repose, we can just estimate from the experimentation or from the typical values given in the table. So tangent of that angle, that will be used in the calculations. On the other hand, we have the other type of spoil bank, which is the conical spoil bank. That means we are placing the soils at some interval. So one cone of the soil has been placed over here, the other cone of the soil has been placed at other places. So in those cases, so the spoil banks are in the conical shape. Okay, in this case, it is the triangular shape, longitudinal triangular. So in those situations, what we need to know is the shape of the spoil bank at the base will be in the form of a circle. So what will be the diameter of that conical shape, and what will be the height of that conical shape, so that we can easily find it. And that is actually based on the volume of the cone. Okay, so here we look at this factor 7.64. This 7.64, actually this factor has come from, I think, pi. Okay, so if you see that there is a in the geometry there is a formula for the volume of the cone. If we apply the same formula over here, we can get the same result over here. Okay, so now volume is equal to 1/3 of the base time area times the height. So volume in this case is equal to 1 times the base area. So the base area will be the pi d square by 4. Okay, so pi by 3, or if we just add, divide and subtract those that values of the pi with that, then we can get the spectra 7.64 and multiply it by the height. So from here we can find the base diameter. Okay, so now we just have to apply these formulas to calculate the quantities. So find the base width and height of a triangular spoil bank containing 76.5 bank cubic meter if the pile length is 9.14 meter. If the soil's angle of repose is 37 degree and its swell is 25%. So we have to find the what we have to find the base width. That means we have to find B, and the height H of a triangular spoil bank. So we have the triangular spoil bank. So we know the formula for the triangular spoil bank, but in this case, remember that. Now I think this is the point. Okay. Remember the soil condition. Okay. Are you listening me? Remember the soil condition. Okay. The soil condition has been given to you is 76.5 bank cubic meter. Okay. 76.5 bank cubic meter. So, but from this bank cubic meter, we have to convert it into its loose condition, because the spoil bank will be in the form of the loose condition. So you cannot simply use this bank condition to find the width and height of the spoil bank in this case. So you took the 76.5 cubic meter in the bank cubic meter of the soil, and then you will have to multiply by its swell percentage. Okay, swell percentage is 25%. So that means when you will remove the soil from the bank condition, it will increase in its volume by 25%. So that's why 76.5 will be multiplied by 1.25, and then it will give the loose volume as 95.6 cubic meter. So now if we will apply this formula, so B is equal to, in this case, so what was the formula? Yeah, 4V, 4 times the volume divided by length times the tangent of the angle of repose in power 1/2. So 4, and then the volume over here is, remember that this volume. So you should not use the bank volume in this case, because the spoil banks are in the loose condition. So therefore, you will use the loose volume. Okay. So the loose volume was calculated as 95.6, and then multiplied by 4 divided by the length of the bank, which was 9.14 meter, multiplied by the tangent of the angle of repose, which is 37 degree. So input these values into the calculator, and then you will find that the width of the spoil bank will be 7.45 meter. So once we find the width of the spoil bank, then we can find the height. Height will be equal to, by this formula, base times the tangent of the angle of repose divided by 2. So which is 7.45 meter multiplied by tangent 30 degree divided by 2. So remember that you can use either the cubic feet units or cubic meter, but I am just following the cubic meter units. So in this case, the height will be 2.8 meters. So 7.45 meter wide. That means 7.45 meter wide and about 2.8 meter high. That will be these will be the dimensions of the spoil bank in this case. Do you have any questions?
No.
Example 2-5. Find the base diameter and height of a conical spoil bank. So this is the example for a conical spoil bank. Conical spoil bank. So base diameter we need to find. That is, we need to find the base diameter and the height h. Okay. And if it contains a 76.5 bank cubic meter, okay, so of excavation, if the soil's angle of repose is 32 degree and its swell is 12%. So in this case, again, we have to convert bank volume into loose volume. So this is the most critical point, okay? If we will just use the bank volume over here in this calculation, then that is not the original condition, because once you remove the soil, once you excavate the soil from its bank condition, the soil expands, and then that soil is converted into its loose condition. So therefore, some sort of swell percentage should be added, and then the loose volume will be used. So therefore, a volume of like a volume excavated as 76.5 cubic meter will become 85.7 cubic meter. Okay, by multiplying by the swell percentage. And then using the formulas for the cones, so we can find that the base diameter of the cone will be 10.16 meter, and the height of the cone will be about 3.17 meter. Okay, the next topic is the estimating the earthwork volume. So when planning or estimating an earth moving project, it is often necessary to estimate the volume of the material to be excavated or placed as a fill. So this is a very, very important step. I think if in many construction projects, so for example, if you are building an airport, okay, on a land, and then we will need to see that that airport is a very large project, and we need to move the soil from that land, or and so that land will become more or less quite leveled. And when that land will be leveled, then we can place the buildings, when we can place the runways on that airport site. So what will be the amount of the earth that will be moved? So that needs to be estimated very accurately. And similarly, also for your capstone project, this may be also a very important task for the calculation of the earthwork volume. So the procedures to be followed can be divided into three principal categories. So the excavations can be classified into three types. One type of excavation can be classified as the pit excavation. Okay, So these are the small, relatively deep excavations such as those required for the basement and the foundations. So a pit excavation. So for example, if you have this column and then you have its base, so then in the from the earth, so then you have to remove this much volume of the soil. So that is volume which is removed, volume of the soil that is removed, that is called as the pit. Okay, so pit is some very localized type of excavation, usually deep and having some a limited amount of length and width. Okay, then there is this trench excavation that is for the utility line. So in the trench excavation, you have like excavation taking place over here. Okay, so this is the excavation. This is the amount of the soil that will be excavated. So this is called as the trench excavation in the lengthwise. And then the excavating or grading relatively large areas. So where there is a very large site over here, such as for the airport, okay, or very large factories or refinery, or so that land has to be leveled off. Okay, so procedures suggested for each of these cases are described in the following sections. Okay, so for example, in the case of the pit excavation, for these cases, simply multiply the horizontal area of the excavation by the average depth of the excavation. So here we can simply find the volume of the excavation by horizontal area by the average depth. So for example, over here, in the case of this column, so for example, if we need a column whose base is 1 meter by 1 meter, okay, so we need an excavation which is at least 1 meter by 1 meter, but maybe for some working area, maybe we can say that maybe 0.2 meter on each side. So maybe we can have like an excavation of 1.2 meter by 1.2 meter. Okay. So 1.2 meter by 1.2 meter will be the base area. And then how deep we have to excavate it, that will be the depth of the excavation. So average depth and the horizontal area. For the trench excavation, what we can use, how we can find the volume of the excavation. So we can, it is also simple, similar to the previous case. We have, what we can do is, we can take the cross-sectional area. That is the, if we are making the excavation like this. So this is the cross-section. So therefore, we can take this cross-sectional area in this form. This cross-sectional area looks like in the form of a trapezoid. Okay, but the excavation can be in the form of a rectangle as well. But of course, side supports will have to be also provided over here. So the cross-sectional area multiplied by the length, so that is length which is along the inside of the plane of this paper. So cross-sectional area and the length. So that means over here, so you can take this cross-sectional area and then the length. So that means how long. That means maybe length L, cross-sectional area times the length. So that is the volume of the excavation in the form of the trenches. And in the form of the large areas, there is this general formula, okay, over here. This general formula says that the sum of the products of the depth multiplied by their sum of the products of the depth times weight. So that means if we take for this large area, if we take several points over here, so we take the depth or the amount of excavation needed at this point, amount of excavation needed at the other point. So at various points, we will find the amount of excavation. And then these amount of excavations will be multiplied by the some weight, okay? Okay, and then divided by the sum of the weight. So this is the weighted average, okay? Weighted average. That means weighted average depth, we find it first. And then weighted average depth is then multiplied by the area of the land to find the volume of the excavation. Okay, so in the form of the large areas. So as a simple example, you can see that over here, estimate the volume of the excavation required in bank measures for the basement shown in figure 2-3. So remember that now we are talking about the excavation. In the excavation, we will be dealing with the bank volume because we are dealing with the natural conditions of the soil, okay? That's why it has been mentioned as bank measures. Values shown at each corner are depths of the excavation. All values are in feet or meters. So for example, at this very simple case, we see that we need to excavate this area, okay? We need to excavate this area. So from A, B, C, D, okay, C, D. So we need to excavate this area A, B, C, D that is over here. But as of now, we only have this information that at A, we need 1.8 meter depth. At point A, we will need 1.8 meter. We need to excavate for 1.8 meter deep. At B, we need to excavate for 2.5 meter deep. At C, we will need to excavate for 2.3 meter deep. And at D, we will need to excavate for 1.8 meter deep. So what will be the total excavation needed, total amount excavated? So for this case, we will find the average depth that we will excavate. So we can simply take the average of these four: 1 plus 2, 1.8 plus 2.5 plus 2.3 plus 1.8. So there are total 4 points, and we are considering equal weight for the points. So that's why the weight for each one is 1. And then the total weight is 1 plus 1 plus 1 plus 1 is 4. So in this case, the average depth in this case is 2.1 meter. So we will assume that the average depth needed is 2.1 meter. Although this land will be something like this. Maybe it may be something like this. So at lower at one point, higher at the other point. So for example, at A, the at A, we need 1.8 meter depth. So at point A. And then at point B, we will need 2.5 meter depth. So to reach to the desired level. So that means at some points, the site is higher. At some points, the site is lower. So depending on these areas, we may, depending on these points, we need different depth. So the average depth needed is 2.1 meter. That means on average, we will excavate 2.1 meter on the site. Okay. So therefore, the total volume excavated will be multiplied by the area. So area is 9.15 meter and times 7.6 meters. So the area is 9.15 multiplied by 7.63. So the total area excavated will be 69.8 square meters. So 69.8 multiplied by 2.1, that is this much volume, 146.6 bank cubic meter volume will be excavated. Okay, 146.6 bank cubic meter volume will be excavated in this case. So this is one very simple example. Another example is this. Find the volume that is in terms of the bank measure of excavation required for a trench. So in this case, this trench excavation. So for the trench, we need the width, cross-sectional area, and the length. For the trench, 0.92 meter wide and 1.83 meter deep. Okay, so it is a deep trench and 152 meter long. So assume that the trench sides will be approximately vertical. So that means approximately vertical sides. Approximately vertical sides. And the picture which I have drawn is not vertical. The sides are approximately vertical. So for the trench, the sides are approximately vertical. Okay, vertical. Okay, so in this case, the cross-sectional area is 0.92 by 1.83 meter. And the volume will be then cross-sectional area multiplied by the length. So this will be 255 bag cubic meter. So that is relatively simple. Another example is this. Okay, find the volume of excavation required for the area shown in figure 2-4. The figure at each grid intersection represents the depth of cut at that location. So depth in parentheses represent meters. So we will have to see this table figure over here. So suppose for this large area, are you listening? Hello?
Yes.
Yes.
Okay. So suppose for this large area, we can divide it into various grids. That means, so we have a total area of something like 121.9 meter long by 91.4 meter wide. And then we have divided this area into several grids. And at each grid, we have determined that we need this much excavation, 1.83 meter, 1.77 meter, 1.59 meter. So we total we have how many points? 1, 2, 3, 4, 5, and then times. So total we have 20 points over here. So in this case, there is a better method than simply taking the simple average of this. So that method is like this. So we have these different values. So we can see that we can identify these all of these 20 points. How many points are here? How many intersection points are here? 20 intersection points. So we can divide all of these points into 3 types. So one type of points are the corner points. That means the points on the corner. So there are 4 corner points over here. There are 4 corner points over here. So since these corner points are occurring only once in the grid, so we can apply a weight of 1 for these points. And the other, there are other 10 points, which are the side points, okay? Which are the border points. Okay, we can call them as the border points. So these points over here, 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 here. So these are the border points. So these are 10 points. So each one of these points is shared by the two areas. So this, so for example, this point is shared by this area and this area, and this point is shared by this area and this area. Okay, but this point is only shared by one area only. That is the corner point. Okay, and in addition, we have 6 more points over here. these are the interior points. So each of these interior point is shared by 4 areas. So for example, this corner, this interior point is shared by this area, this one, and that one. This area is also shared by this one, and that one. So using the, I think this is also based on the trapezoidal rule or the Simpson's rule of calculation of the areas, that what we can do is we can take the corner points over here, and we can also take the border points over here. We can add them all together. We can take the interior points over here, and then we can find their average depth. How we can find the average depth? We can take the sum of the corner points and multiply it by its weight, which is equal to 1. So of course, 15.4 times 1 will be 15.4. We will take the border points, and the sum of the border points was 43. That is 13.12 meter. Okay, the sum of the border points was 13.12 meter. The border points will be multiplied by 2. Why? Because as I have just said that each of these border point is shared by the 2 areas. And similarly, we will take the interior point, sum of the interior points, which is 8.01 meter, and multiply by 4, because each of the interior point is shared by the 1 area. So what is the sum of the weights? Because there were, I think there were how many interior points? So there were 4 corner points. So multiplied by 1, that is 4. 10 border points. Multiplied by 2, that is 20. And 6 interior points. Multiplied by 4, that is 24. So 24 plus 20 is 6 times 4 is 24. 24 plus 12, 20 is 44. 44 plus 4 is 24 plus 48. And here we are dividing by 52. Why? Okay, so here the corner points are here, border points are here, interior points are here, and average depth will be 48. Let me see if I'm making any mistake. How many border? 3 plus 3, 6. 6 plus how many points are? 6 plus 4 is 10, right? And 4 corner points. Yeah. And 4 corner points, and then interior points are 6. So 6 times 4 is yes. 48. I think it should be 48 actually. Maybe there is some mistake over here. Okay. So anyway, so we will. I think it should be 48. Because 6 times 4 is 24. 10 times 2 is 20. Well, I think 4 times 1 is 4. So 24 plus 20 is 44 plus 4 is 48. It should be 48. Yeah. So the interior point. So because if you see that the formula is this. Okay. Sum of the products of depth times weight divided by the sum of the weights. Okay. So the sum of the weights is this. Yeah. So it should be 48 anyway. So whatever will be the answer, then that will be multiplied by the area. So the area is 91.4 meter by 121.9 meter. Yeah, 921.9 meter by 91.4 meter. So that will be the volume, and then that will be the area, 11,142 square meter. And then that will be multiplied by the average depth needed. So it will be 13,482 blank cubic meter volume will be needed. So therefore, sum of the weight. Okay, so it's for the amount of excavation needed, amount of excavation in large area. So the amount of excavation needed in the large area, we will need to find the what are the corner points, what are the border points, what are the interior points, and then each interior point will be multiplied by 4, each border point will be multiplied by 2, and then plus each corner point will be multiplied by 1. Okay, so the sum will be like that. So in this way, you will find the earthwork, estimate the earthwork volume. Okay, so this is this small quiz. So what is this? Earthwork involves moving and processing of soil or rock to meet the construction requirements. True or false? So this is for you to answer. An equipment utilization plan must be developed for effective use of equipment on the project. Production rate of an earth moving equipment is the total production of the equipment in a day. Loose granular soils are highly loadable and trafficable. And silt particles pass the number 200 C but are larger than 0.002 millimeter. True or false? And the poorly graded sand has an excellent drainage and good suitability for surface. So I think you should review this topic and then you can find the answers of these quizzes. So with this, this topic is completed. And do you have any questions?